How's it going? This is Mike coming back at you here with another video on number theory. In the previous video, we talked about the greatest common divisor, or GCD, of two integers a and b. We talked about the definition of it. We talked about properties of divisibility as well. And then we saw some interesting facts and theorems that involve the GCD. We talked about two numbers being relatively prime and the special definition there. In this video, we are going to build upon the previous video. In the previous video, we just learned about the GCD of two integers a and b, and we know that we have the GCD of these two numbers, but the question is, how do we find it? And that's what we're going to talk about in this video. We're going to learn about an algorithm that will help us figure out what is the GCD of two numbers. And that algorithm is called the Euclidean algorithm. And when I say we're going to find the GCD of two numbers, we're now going to work with some larger numbers. You've had practice prior to high school with finding the GCD of two smaller numbers, like, say, 40 and 10, kind of basic, kind of a trivial, where you just list out all the factors and then see whatever common factor is the largest. We're talking larger numbers, like 3 digits, 4 digits, 5, even higher. So suppose we had 9,720 and 798. What is the GCD of those two numbers? Well, this algorithm is going to really show us how we would find the GCD of those two numbers. So we have two integers a and b. We're going to assume that a is greater than b, and we're going to find the GCD of these two things. Well, by the division algorithm, I can write a as some integer q1 times b plus r1. So a is equal to some quotient times b plus some remainder, where r1, our remainder for this first use of the division algorithm, is greater than or equal to 0, and it's also strictly less than b. The nicest case is that when you do this, r1 is equal to 0. If you have no remainder, then you just have a is equal to q1 times b. That r is gone, and this says that b divides a, and thus the GCD of a and b is going to be b. But in many cases, that's not quite the case. Many times we'll see that this first remainder is non-zero. So what do we do if the remainder is not 0? Well, we're going to use the division algorithm once again, but we are going to do it with slightly different numbers, and or these numbers will be in a slightly different place. If you have to use the division algorithm once more, your b value, when you do it a second time, is going to take the place of your a value. And your radius, your remainder, r1, is going to take the place of your b value. So b becomes new a, remainder becomes new b value. So we're going to do the same thing now. We're going to write b as some whole number, q2, times my new b value, actually r1, plus some new remainder, r2, where r2 is greater than or equal to 0, and r2 is strictly less than r1. Now, if r2 is equal to 0, then B is equal to Q2 times R1, and that works out nicely, and we would stop, and that would be it. Otherwise, we're going to keep going through the same set of steps, if you will. And when I say set of steps, we're really just talking about one step here. We're going to keep taking our new B value, in quotes, and having that become our new A value. And then our remainder is going to become our new B value. So if I had to do this once more, if R2 was not equal to 0, we see that we have R1 now taking the place of my B, or what was at the very beginning A, and my new remainder, R2, is taking the place of the R1, which took the place of my B value to start with. And we keep going through this whole thing until we get down to the end here. We have some remainder is equal to some quotient times the next remainder plus a new remainder, r sub n, and then you find that r sub n minus 1 is equal to q sub n plus 1 times rn plus 0. And this list of steps, this list of calculations, this repeated use of the division algorithm is the Euclidean algorithm. Now, how does going through this process of using the division algorithm however many times tell us what our GCD is? The last non-zero remainder that you get in the Euclidean algorithm is the GCD of your two starting numbers, A and B. So you look at the second last line, and you look at the remainder in that second last line. That number, whatever that is the GCD of the two numbers that you began with, A and B. Now, why does this work? How can we say that by changing the A in quote values and the B in quote values to be these new remainders that we're getting throughout this process, what lets us say that, okay, what we're going to get in the end as some remainder is the same as the GCD of the two numbers that we started with all the way back at the very beginning of this process. And what lets us do that is the following lemma. If A is equal to Q times B plus R, then the GCD of A and B is equal to the GCD of B and R. So this is where the moving of terms, having terms take the place of other terms as we go down, that's where this comes in. And that's what lets us say that the GCD of A and B is the GCD, or is that last non-zero remainder. We're just using that lemma over and over and over and over to come up with our GCD. That's the general theoretical formula for it. Let's actually do this with some numbers. Let's do a specific sample problem here that will add a bit more clarity to this. In the next video, we're going to do a few more sample problems of seeing how we calculate the GCD of two whole numbers using this algorithm. So here's my one example for this video. We have the numbers 12,726 and 3,024. I want to find the GCD of these two numbers. So the Euclidean algorithm, which is essentially just repeated use of the division algorithm, is what we are going to use here. So let's kick that off. 12,726. How many 3,024s can I take out of that? I can take 4 of those out, and I'm left over with 630. So 12,726 is equal to 4 times 3,024 plus 630. Now, here's where the switching of terms comes in. We see that my b value takes the place of my a value, and the remainder takes the place of my b value. And now we're doing the same thing. We are using the division algorithm once again, but now our numbers are 3,024 and 630. So how many 630s can I pull out of 3,024? I can pull 4 of them out, and I'm left over with 504. So that's why we say 3,024 is 4 times 630 plus 504. Once again, we're going to do the same substitution of values. My b value takes the place of my a value, and my remainder takes the place of my b value. So now we're doing division algorithm now with the numbers 630 and 504. You can get one 504 out of 630, and you're left over with 126. So we write that out, and as we're going to see one more time, the b value takes the place of the a value, and the remainder takes the place of my b value. So we are doing division algorithm once again with 504 and 126. Now, how many 126s can you pull out of 504? You can pull out 4 of them, and you have 0 left over. So 126 divides 504. So we write out this last line of 504 is equal to 4 times 126 plus 0. We said that the last non-zero remainder was the GCD. So we're going to go back up one line. We're going to the second last line. And we look at the remainder there, which in this case is 126. And that is the GCD of 12,726 and 3,024. You could do this in your calculator if you wanted to. If you wanted to waste a lot of time, you could try and come up with all the factors of 12,726 and 3,024 and see that 126 is the largest of them. But I can promise you, you'd be doing that for a long time. So I would not recommend that. But this is one way that we can find the GCD of 2 whole numbers. Later on in the course, we're going to find out another way that we can figure out the GCD. That's kind of a neat little way. But where we're at so far, this is a nice, easy, straightforward way to figure out our GCD. Yes, it is a bit repetitive. You do have to be careful about what values you're using for the next step. If you use the wrong values, then the problem is going to fall apart, and you probably won't get to the correct answer. So just be very careful on that. But as I said, this is just one sample now for this video. In the next video, we're going to do a few more sample problems here, and we're going to see a few more samples of finding the GCD of 2 whole numbers. And we will be working with larger numbers, numbers that have 4 digits, 5 digits, and perhaps even 6. If you have any questions or comments, be sure to drop them in the comment section below. Otherwise, until the next video, take it easy, guys.